This is the last of our lectures on Greek mathematics, and in this lecture I'm finally going to start talking about astronomy. As I said, astronomy has been one of the dominant moving forces behind the development of mathematics. And in this lecture we're going to look at how astronomy led to the development of trigonometry. Now, most people think of trigonometry as something that's used for land measurement, and certainly today it is used in surveying. But that's not where we get trigonometry. Trigonometry actually comes to us from astronomy, from problems in astronomy that I'm going to talk about in this lecture. And its application to problems of surveying actually didn't come about until quite recently. The earliest actual reference that we have to the use of trigonometry for the purposes of surveying is a book written in 1595 AD. For most of the history of the development of trigonometry, it came from astronomy, and it was being used exclusively in order to study astronomical phenomena. We also think of trigonometry as being defined in terms of the ratio of the sides of a right-angled triangle. Again, that's not the way trigonometry has been thought of. That's not the way people have thought of the trigonometric functions, the sine, the cosine, and the tangent function throughout most of the history of mathematics. We're going to see that those functions come out of the problem of trying to determine the length of a chord of a circle, finding the distance, the straight line distance between 2 points on a circle. And this idea of defining the trigonometric functions in terms of ratios of sides of a right-angled triangle only comes about in the 18th century. Trigonometry is extremely important, not just for the trigonometric functions and the role that they're going to play in mathematics in many different ways. That turns out to be one of those abstractions that is extremely important in many different contexts. But they also really begin to introduce the idea of function, and I'll talk more about this in this lecture and then again in the next lecture. This idea of having a process where you can take an input that can be any real number whatsoever, and you need to have a well-defined output no matter what input you put into this function. Well, I need to start by thinking about the solar system, and most of us have a picture of the solar system. There is a standard picture where you see a bunch of balls. There's a bright yellow ball in the center that represents the sun, and you've got a small blue ball, which is the Earth, and you've got a little red ball, which is Mars, and you've got all of these balls that are lying out there. And you see nice elliptical paths that are marked out, and the planets are going in these nice elliptical paths around the sun. And some people wonder, how could the ancients have been so confused that they didn't realize that the planets go around the sun? And of course, this traditional picture of the solar system that we have is something that nobody has ever seen. Nobody has ever actually put a satellite into that position and taken a picture of the solar system. And even if they did, that's not what they would have seen. The planets are much too small to show up as nice round balls. They simply would be dots of light. And planets don't leave vapor trails as they travel around the sun. You don't get these nice elliptical paths coming out. What the astronomers have seen is simply the night sky. And it's important to begin by thinking about what you can see in the night sky and how the astronomers began this process. The first thing that you observe by looking at the night sky is that the relative position of the stars is fixed. And this is why we create the constellations, why we're able to identify constellations, certain groupings of stars that always stay in the same relationship. But even though the relative position of the stars stays fixed, the stars themselves are moving in the sky throughout the night. And in fact, if you take a time-lapse photograph pointing toward the north, what you will see is that the stars are actually moving. You can see the tracks of these stars over time. The one star that stays fixed is the North Star or the polar star. That does not move. But all of the other stars are turning in a great sphere, a great celestial sphere around this North Star. One of the things that was observed in antiquity, far into prehistory, we have no idea when this first was observed, but the fact that the sun does not have a fixed position against this dome of the stars, that in fact the sun is constantly changing its position, and you can see that in that the first stars that you see on the horizon at sunset, or the last stars that you see on the horizon at sunrise, are going to be different constellations at different times of the year. And it was quickly realized that the position of the sun against the dome of the night sky is very important. Knowing where the sun is located tells you where you are in the process of a year. So it tells you when to expect the rains, when to expect spring to come. It tells you when to plant and when you should expect that the harvest is ready to be brought in. So the position of the sun against the heavenly dome is an extremely important thing to be aware of. And the actual path of the sun is what we call the ecliptic. And that comes from the means that people found, astronomers found, for determining where the sun is located. It's very difficult to see where the sun is against the stars because when the sun is out, it's so bright that you can't see the stars around it. But ancient astronomers figured out the path of the sun by using lunar eclipses. When the sun, the earth, and the moon are all lined up, the moon is exactly at the opposite point of the sky from where the sun is located. And so the moon, during a lunar eclipse, the moon is located where the sun will be exactly 6 months in the future. And by realizing this, then astronomers were able to gradually plot out the points where the sun would be at different times of the year. And once you begin to collect lunar eclipses over a period of 700 years, you get a very accurate track of where the sun is. And the position of the sun at different times in the year then tells you what to expect from the seasons. What we get are the signs of the zodiac, which are references to the constellations, which give a rough idea of where the sun is located. And there's a nice illustration of this in a frontispiece from Ptolemy's great work, the Almagest, that I'll talk about a little bit later in this lecture. And what you see in this frontispiece is what's called an armillary sphere. And so it is an object that shows the relative position of the sun and the various stars. The Earth is located in the center of the armillary sphere. You see the band of the ecliptic, that's the path that the sun moves along. And you also see the signs of the zodiac on this armillary sphere. Now, there are a number of problems that come up with the ideal situation for what's happening with the motion of the sun and what's happening with the stars. One of the things that was observed fairly early on is that in addition to the fixed stars, there are stars that move. In Greek, they became known as the wanderers or planetes, from which we get our word planet. So the planets are the stars that move, and it was observed that these stars that move also follow the ecliptic. And to the ancient astronomers or astrologers or mathematicians, again, those three terms really are synonymous, they observed that these points of light followed the same path as the sun. And if the position of the sun was so important for what's happening on Earth, then the position of these smaller lights must also be important for what's going on the Earth. Now, they're much smaller than the sun, and so one would expect their influence to be much more subtle. But nevertheless, they should have an important influence, and this is why astronomers, astrologers started tracking the position of the planets to figure out what's going on. Now, this was Aristotle's view of an Earth-centered universe, with a great sphere of the stars, the sun, and the planets traveling on this path of the ecliptic. But it ran into some problems, and one of the first of these to be observed was the problem of retrograde motion. the fact that the planets do not keep moving along this great curve of the ecliptic. Every once in a while, they will slow down and back up. And this was a problem that Aristotle put out to the scientists of that time, the mathematicians and astronomers of that time, to explain what's going on. If in fact we have circular motion going out in the heavens, why do the planets occasionally stop, back up, then stop again and start going in the original direction? We understand this phenomenon today because we realize that a planet such as Mars is circling the sun, not the Earth, and the Earth is also circling the sun, and the Earth is closer to the sun, and so it takes less time for the Earth to go around the sun. And what happens is, every once in a while, the Earth is going to lap Mars. So when the Earth comes closest to Mars, it's actually going to pass it, and it's going to look like Mars is backing up. But then once the Earth is far enough along, it will again look like Mars has begun moving in its normal direction around, in this case, around the sun, or what it looks like from the Earth, that Mars is going around the Earth. This problem of trying to explain retrograde motion, this backing up motion of the planets, something that Aristotle posed, and as the first person to come up with a solution was Aristarchus of Samos. He was born sometime around 310, and Aristarchus suggested that maybe retrograde motion is coming from the fact that Mars does not go around the Earth. Maybe Mars and the Earth both go around the sun. He actually came up with the correct solution. But of course, nobody believed him because his solution was totally preposterous. There's no possible way that the Earth could actually be circling the sun. We would have to be traveling at incredible speeds. In fact, the speed of the Earth around the sun is about 67,000 miles an hour. How could we possibly be traveling around the sun at that kind of a speed and not be aware of it? So people began to look for other solutions. And the person who eventually would come up with a solution to retrograde motion that would generally be adopted was Apollonius of Perga. This is the same Apollonius that we met in the last lecture, famous for his work on conics. And he's the one who suggested that what's really going on is that as Mars circles the Earth, Mars itself is actually located on a little circle whose center circles the Earth. So what happens is that we have Mars, which is going around and around a little circle, and the center of this little circle is going around the Earth. And so what's actually happening is that Mars executes a kind of looping motion as it travels around this little circle called an epicycle, so an outer circle. It goes around this little circle, the epicycle, as the center of the epicycle goes around the Earth. And this preserved one of the foundational Aristotelian viewpoints about the nature of the heavens, which was that everything that goes on in the heavens must be built out of circles. Now, there are other problems with trying to explain what goes on in the heavens, and another one of the problems that actually was observed by Aristotle and finally solved by Hipparchus of Rhodes, who lived sometime in the 2nd century BC, was the problem that if you look at the length of the seasons, they are not of equal length. So the ancient astronomers knew where the sun was located at the summer solstice, and they knew where the sun was located at the winter solstice, and these 2 points are exactly opposite along this great circle of the ecliptic. You then look at right angles from the line that connects the summer solstice to the winter solstice, and that gives you the vernal equinox or the spring equinox and the autumnal equinox. And the seasons are marked by the time from the winter solstice to the spring equinox. That gives you winter. Spring equinox to summer solstice gives you spring. Summer solstice to autumnal equinox gives you summer, and so on. And one would expect, if the sun were just traveling in a nice big circle with the Earth at the center, that each of the seasons would be the same length. But they're not. Now, it may not seem this way, but actually winter is the shortest season and summer is the longest. And the difference between the two is not subtle. Winter is about 89 days long from the winter solstice to the spring equinox. Summer is more than 4 days longer. It's 93 and about 5/8 of a day. So it's more than 4 days longer from the summer solstice to the autumnal equinox. And it was Hipparchus of Rhodes who came up with the idea of how to explain this. It could be explained if, rather than putting the Earth at the center of the universe, you had the Earth slightly off-center. So if the Earth is slightly off-center, if it's closer to where the sun would be in winter, then you're going to get a smaller arc that the sun has to travel during winter, and you're going to get a longer arc that the sun has to travel during summer. Now, of course, this immediately begins to upset the Aristotelian worldview because it moves the Earth off the center of the universe, but that seems to be the way to do it. And Hipparchus was looking at this problem and trying to figure out how off-center the Earth had to be. And that's where we get to the problem of calculating the length of a chord. In order to do this, Hipparchus essentially invented trigonometry. What he did was to invent a way of determining the length of the chord that connects 2 points on the arc of a circle. So this would become the basic problem of trigonometry. You've got an arc of a circle, and you want to figure out the length of the straight line that connects the 2 points at the end of that arc. Now, first of all, you've got to decide how you're going to measure that arc of circle, and we measure it in degrees, and this has been inherited from the Babylonians, who measured the arc of a circle in degrees. And this is something else that people very often do not understand. Today we use degrees to measure how much something has turned. We say that something has turned 90 degrees, that means it's made a quarter turn. That is very recent. That's an 18th century interpretation of degrees. Up until the 18th century, degrees were a measure of arc length. They were a measure of how far you had traveled around the outer edge of a circle. And the Babylonians divided the circle into 360 degrees, almost certainly because that's approximately the number of days that it takes the sun to travel completely around the Earth, or the Earth to travel around the sun. Interestingly, the Chinese divided a circle into 365¼ degrees. And this is nice in one respect because it means that the sun moves exactly 1 degree every day. But working with a circle of 365¼ degrees is very difficult to do. And so the Babylonians made a compromise. They picked an easier number to work with, 360. What that means, though, is that the sun does not move exactly 1 degree across the ecliptic every day. It moves a little bit less than 1 degree every day. These degrees of arc length, then, would be subdivided, according to the Babylonian system, into 60ths of a degree, which we call a minute. And the word minute actually comes from Latin. It means a small part, pars minuta. And so we take the word minuta and it became in English minute. And then you divide the minute up into 60 seconds of arc, so a 60th of a 60th of a degree. And this is called in English today a second. And this comes from the phrase the second small part, pars minuta secunda. And so secunda, the second small part, became our second. So we're measuring the arc length in degrees, minutes, seconds. And given any particular arc length, we want to find the length of the chord that connects the 2 endpoints of that arc. Now, that's going to depend on the value of the radius. So as I make the radius larger, the chord length is going to change. So the chord length is always described in terms of the radius. If I take an arc of 90 degrees, that's a quarter of a circle. And if I know the radius, it's simply the length of a diagonal. And so the chord of 90 degrees of arc is going to be the radius multiplied by square root of 2. If I take a chord that corresponds to an arc of 60 degrees, well, I simply get an equilateral triangle formed by the two radial lines that go out to the circumference, and so the chord of 60 degrees is exactly one radius. And the Greeks were also able to figure out the exact value of a chord of 72 degrees. That turns out to be the square root of the quantity 5 minus the square root of 5, all divided by 2. Now, I've said that this problem of finding chord lengths is where we get trigonometry, and in fact, trigonometry does correspond to these chords. If we think about taking an arc and then taking the chord that connects the two endpoints of the arc, and the terminology here is the terminology of bows and arrows, so an arc or a bow, we've got the chord or string that connects the two endpoints of that arc, and we consider the line from the center of the circle out to the midpoint of our arc. And that was referred to as the arrow. It looks very much like an arrow. We can now connect the radial lines that go from the center of the circle down to the bottom of the arc and the center of the circle up to the top of the arc. And it really does look like a bow and arrow at this point. And if you consider not the full chord length, but only half of the chord length. So you consider the chord that goes from where it attaches to the arc at the top down to the arrow. What you have there is precisely the sine. Now, the Greeks did not work with the sine. The Greeks worked with what today we would think of as twice the sine, the chord. And this idea of working with half of that quantity, working with the sine, is something that would come out of India. And I will talk about that in the next lecture, how Indian astronomers picked up the ideas of Hipparchus and the other Greek astronomers, and then developed them into the kind of trigonometry that we understand today. Instead of working with a full chord, they worked with a half chord, what they called the sine. And then you also get the other trigonometric functions, the cosine. The tangent itself actually would be invented by Islamic astronomers. In the time that remains, I want to talk about the greatest astronomer of the Hellenistic period and also one of the greatest mathematicians of this period, and that is Ptolemy of Alexandria. We've run across a number of Ptolemies before, Ptolemy the first, second, and third, who were rulers in Alexandria, rulers of Egypt. This is a scientist who happened to share the same name. He lived during the 2nd century AD, and he took the ideas of Hipparchus and he put them into an incredible work on astronomy, a work that runs to 13 books, a work that is so comprehensive, does such a great job of explaining astronomical phenomena, that just as when Euclid's Elements came out, people threw away any mathematical works they had from before Euclid, the same is true with Ptolemy. When Ptolemy's astronomical work came out, everybody threw away any other astronomical texts that were out there. And so none of the texts from before Ptolemy actually exist. All we have are a few references to what was contained in them, and it's Ptolemy's own references to Hipparchus that tell us what Hipparchus had been doing. This great work of Ptolemy was known as the Mathematikis Syntaxis, the mathematical collection, and it would come to be known as the Great Collection, the Megisti Syntaxis, and the Islamic astronomers would then translate this into Arabic, and they would come to know it simply as the Great Work, Al-Magisti, taken from Megisti Syntaxis, the Al-Magisti. When this then was translated from the Arabic into Latin for European astronomers and European scientists, they took the Arabic term, the Al-Magisti, and they called the work the Almagest. And so that's the term by which it is commonly known today. And one of the great results that Ptolemy was able to do in this book, there's a lot of astronomy in it, there's a lot of mathematics in it, but I want to focus on one part, which is Ptolemy's efforts to construct a table of values where you could put in the arc length that you were interested in and then read off what the chord length would need to be. As I said, he started with certain chord lengths that were fairly easy to determine. And of course, one of the things that you've got to decide as you come into this is what your radius is going to be. Now, the circumference of a circle is 360 degrees. And it's going to be easiest to work with chord lengths if we measure the chord length in the same units that we use to measure arc length. So we really want to measure the chord length in degrees. Well, if I've got a circle of circumference 360, that means that I'm going to need a radius which is 360 divided by 2 pi, which is a little bit more than 57 degrees. It's about 57 degrees, 17 minutes, 45 seconds. Well, that's very difficult to work with. So what Ptolemy and the other early astronomers usually did was to convert everything to minutes. So the total circumference of the circle would be 360 times 60, and then the radius in minutes is approximately 3,438. Now, what Ptolemy was able to do then was to take the values of chord length that he knew. He knew the chord length for 72 degrees. He knew the chord length for 60 degrees. He also was able to work out how the chord length of a given arc could be determined if you knew the chord lengths of 2 arcs that added up to that. Or equivalently, if you know the chord length of 1 arc and you know the chord length for a smaller arc, he found the formula for finding the chord length of the difference. This is equivalent to our modern formulas for finding the sine of a sum of angles or the sine of a difference of angles. And so using these, he was able to find an exact value for the chord length of 12 degrees. And then you can also use this formula if you know the chord length for a given arc. You can find the chord length for half of that arc. So once you know the chord length for 12 degrees, you can find the chord length for 6 degrees or 3 degrees, or 3/2 of a degree, or 3/4 of a degree. But that doesn't give you the chord length for 1 degree, and this is something that Ptolemy really wanted to work out to quite a bit of accuracy. And one of the advantages of using the same unit of measure to measure the arc length and the chord length is that as we take smaller and smaller arcs, the ratio between the chord length and the arc length should approach 1. And so for very, very small arcs, we can assume that they're approximately equal. And that means that the 3/4 degree arc divided by the chord of 3/4 should about equal the arc of 1 degree divided by the chord of 1 degree. And that tells me that the chord of 1 degree is very close to the reciprocal of 3/4, which is 4/3, times the chord of 3/4. He knew the exact value of the chord of 3/4. He could then use that in order to find a very, very close approximation to the chord of 1 degree. And once he had the chord of 1 degree, he could find the chord of 1/2 degree. And once he had the chord of 1/2 degree, and he had this formula, if you know the chord of 1 arc length and the chord of another arc length, you can add them together. So he was able to build up an entire table of chord lengths in intervals of 1/2 degree. And if you know the chord length for 1/2 degree, that corresponds to the sine of 1/4 degree. So effectively, what Ptolemy was able to construct was a table of values of the sine down to just 1/4 degree at a time. Now, Ptolemy was 2nd century AD. As I've said, Greek mathematics really ends about 400 AD. Fortunately, though, this was not the end of the developments in astronomy, because these astronomical works that came out of the Eastern Mediterranean would be imported into India, and the Indian astronomers would pick up this idea, carry it much further, and also bring in many new ideas in mathematics. And in particular, one of the things that we will see in the next lecture is how this work on trigonometry would lead to a general appreciation for polynomials.